Okay, so we have a number of partners, both small and medium-sized companies and government partners. And this is a kind of high-level overview. This is somewhat shifting ground, but this is so currently how we view the task ahead of us. There are problems in data collection, which include collection from mobile platforms. I won't talk so much about that right now. Problems in early vision, which require us to detect and segment interesting things like people, vehicles. There's problems of improving the 3D reconstruction phase, but also in being able to extract analytics about dynamics. So particularly we're focused on human movements and traffic movements. And then, of course, this is the big, hopefully the big payoff, being able to integrate this into a 3D dynamic model. So it's a kind of an ambitious plan, but I think we want to know what we're working toward. I obviously don't have time to talk about all these problems, so I'm going to focus on what I think are four interesting components. These are not in any way sufficient to bring off what I'm claiming we'd like to do, but I think they're necessary. So I think there are four critical components. And I'm going to start by talking about the work of Gunho at York. So I'll call this component one. This is trying to develop enriched urban environment models, which could be subtitled Trying to Correct Google's View of York University, because this project is partly linked to the York 50 celebration. So this is the 50th anniversary of York University. And so Gunho's group is busy trying to three-dimensionalize the university in the spirit of York 50. So I'm going to briefly talk about this work, but I apologize to Gunho for any mistakes I made. If you have questions about this part, please talk to Gunho. But I'll briefly show you the sort of things here. So the problem is to try to develop not just a Google Earth style model of York, but a better than Google Earth style model of York University. So one of the ways in which this will be better is that it will include both outdoor and indoor modeling. Okay, so you'll be able to walk along the corridor and then into or fly into a building. So that's a major advance. There are various steps to this modeling, so it includes the indoor modeling, facade modeling, so superior texture models of buildings, and then rooftop modeling, texture mapping, modeling of foliage, for example, which is something we don't have in Google Earth, and then web integration. So this is a very quick overview. Gunho's using a large variety of sources, including LiDAR, through Optech, various kinds of ortho images, DMs and so forth through first-place solutions, some stereoscopic data from the city of Toronto. You can see this. These are actually floor plans, cleverly drawn in pale blue on white here, but anyway, those people in the front row can see there's floor plans of various universities, which are various buildings, which are important for the indoor modeling. And then this is all brought together through a variety of software tools. So some of these are off-the-shelf tools, like Google SketchUp or the Modeler, VDS Max. But an important thing here is that we're trying to work toward greater automation. So Gunho's working with in-house, sort of an organically growing in-house software environment, which uses principles such as description length to automate a lot of this construction. It's still semi-automatic, of course, but the idea is to make this a more efficient process. So through this, we have the development of indoor models, outdoor models, and the integration of indoor and outdoor models into one model, and then integration within Google Earth. So we have the more or less flat EM provided by Google Earth, and we have buildings populating it. So I don't have time to do much more than just show a very quick fly-through through York. So you'll see, this is, for those of you who know, this is the York Common. This is Barry Hall here. His primary purpose is to hide the 1960s architecture with the Ross building behind it. Anyway, so you can see the Tennis Canada Centre there at the top coming into view. Okay, so the plan is to have, this is not live yet in public, I guess. Not live yet, right?
Live.
It is live. So I should have put the URL there, but you can get a URL for it. Okay, so so that's component one, and I think this is very exciting work there. But let me move on to maybe what's the focus of my talk, which is dynamics. So York wouldn't be much of a university if there wasn't some movement happening. And so, for example, here is a sort of typical view from a security camera at York. So like most universities, we have them all over. We have over 400 security cameras at various locations at York University. Some of them, of course, are showing pedestrian traffic, some vehicle traffic. One of the important things about these cameras, which is typical of many urban cameras, is that they're pan tilt zoom. Okay, so that's good because it's flexible. You can move it around and get different information. It's bad in the sense it makes our life more complicated because there's no opportunity to pre-calibrate these cameras. And that's actually the first component I want to talk about. So this is work going on in my own lab at York. This problem with camera calibration. So in order to three-dimensionalize video data, basically the first thing we have to do is at least understand how the camera is pointing in 3D in relation to the three-dimensional model. And that would be a lot easier if these cameras were fixed in space, but simply they're not. Both their external orientation and their internal parameters, the focal length is changing. So it's impractical to pre-calibrate. So we have to be able to do online calibration using computer vision techniques. So the first question is this possible? And the answer is it's more possible in urban environments than in many other environments because urban environments have typically a lot of structure, a lot of linear structure. And so there's an opportunity to use what we all understand as linear perspective. Now, you might think, well, didn't we figure this out 500 years ago, how to use linear perspective? And it's true that in the time of the Renaissance, artists and scientists, philosophers as they were then called, figured out what we call the forward problem. That is, if I have a three-dimensional scene in my head, how do I render it on a two-dimensional plane in order to be geometrically accurate? So now we're just 500 years later, we would like to understand what we call the inverse problem. That is, if we have a two-dimensional image, how can we, from that image, understand what the three-dimensional orientation of the scene, the objective image, should be? So we want to solve this problem, not in general, but for urban environments. And to do that, we're going to make use of something it's usually called the Manhattan assumption. So we sometimes call this the Manhattan Project, which is that in urban environments, you typically have three canonical directions. Vertical, obviously, and then typically you have sort of streets and avenues. So there are two canonical horizontal directions to which the buildings align. This isn't always the case. It's more true in North America, of course. But this is a very powerful constraint. So to the degree it holds, it can be used to help to auto-calibrate the camera. So this is the so-called Manhattan Project.